Hello everyone. Let's get started. So welcome to another lecture as part of our course ME6151 Computational Heat and Fluid Flow. So in the last lecture or in the previous lectures, we have been looking at gradient calculation methods. And we looked at two different methods of gradient calculation. One was the Green-Gauss or the gradient theorem approach, and the other one was the least squares approach. The motivation to look at the Green-Gauss or least squares approach, these gradient calculation methods, was that we needed to calculate grad of phi, right, which was required not only by the secondary gradients that we got as part of the unstructured non-orthogonal mesh, but also the gradients of the phi are required from different perspectives, right? Either if you have looking at a turbulence modeling, or if you are working with a non-Newtonian fluid, or if you are looking at a larger simulation, all these things would require you to calculate the gradient of the dependent variable, grad u or grad phi, and so on. So as a result, we had to calculate gradient at the cell centroids. Okay, then we looked at these two methods. In the Green-Gauss method, we used the gradient theorem approach or the Green-Gauss theorem, wherein the volume integral of the scalar is written as a surface integral, right? And then we calculated what is the gradient. And in the least squares approach, we found a least squares error fit for all the data points, and we found one simplified matrix, that is A transpose AG equals A transpose D, right? That was a kind of a 2 by 2 matrix that we have to solve at each and every cell in order to obtain this vector G, which is basically partial phi, partial x, and partial p, partial phi, partial y. Okay, so we kind of discussed these things in the last lectures. So let us move on. And so in today's lecture, we're going to look at the influence of secondary gradient on the coefficients. So up till now, we have been saying only that the secondary gradients will make that the solution may not be bounded, right? The guarantee that the solution is bounded will be taken away if you have secondary gradients, is what we have been saying till now, but we have not actually proved it or looked into why it may happen so. So that is one thing we're going to see today. And other thing we're going to look at is how do you implement a solution procedure, or how do you program it, the solution procedure for solving a diffusion equation on unstructured mesh. Doesn't matter whether it is a orthogonal mesh or a non-orthogonal mesh. So only if you have, as long as you have an unstructured mesh, can I go ahead and implement it, and what is the way if it is to be done. Okay, so this is another thing we're going to look at in today's lecture. So let's so that means the broad questions we address in today's lecture are: the first one is that boundedness is not guaranteed even if the source terms are absent in the context of unstructured non-orthogonal meshes. Why is it so? Why is boundedness not guaranteed? That is the first question we will address in today's lecture. And after finishing that part, we will move on to how do I program for diffusion equation on unstructured meshes. Okay, is it the same way I would program on a structured mesh, or is there something different? Is there something that can be done differently which will enable us to run the program with, let's say the program will be faster, or it can be a little more memory efficient, or it can be better from the algorithm point of view. Okay, so all these things we will kind of consider, and then code, how do I code for diffusion equation is the second question we will address in today's lecture. Okay, so by the way, this is this how do I program is how it is done in all the software that are out there. Okay, so this is the same method that we're going to discuss, which is basically belongs to the unstructured solution methods. All right, let's move on with the first question. Let us look at the influence of secondary gradients on the coefficients. Okay, so here we consider on the left hand side we show a mesh here. This is basically what I would like to call it as a curvilinear mesh, but that is uniform. So that means these cells are pretty much uniform. They are of the same size approximately, but then the mesh need not be orthogonal. Okay, the mesh is non-orthogonal. For example, if you connect the cell centroids, the area may not be in the exact same direction. So we are choosing this simplified geometry in order to understand the effect of influence. So we are looking at a uniform mesh that is need not be orthogonal. Okay, that is non-orthogonal. So as usual, we have our cell P. Okay, that is right here. And it also has the east cell, west cell, north cell and the south cell. Okay, and we also have the corner neighbors here, which are the northeast, northwest, southeast and southwest. And also we have the east face, which has two vertices A and B. This is the same nomenclature we have been following till now. And we also have these blue lines, which are basically eta equal to constant, and the black lines, which are basically xi equal to constant. Okay, that means if you move along this xi equal to constant, eta increases, and if you move along this eta equal to constant, xi increases. Okay, so the secondary gradients would lead to the calculation of partial phi, partial eta on the east face, right? Now, how do we calculate this? We looked at this calculation methods a while back. We can do it in two ways. One is basically calculate what is phi A and phi B, essentially interpolate phi A from its neighbors, that is P, east, southeast and south, and interpolate phi B from P, east, northeast and north, and then using these interpolated values at A and B, we can calculate what is partial phi, partial eta in this direction on this face E, right? Now, another approach is, of course, to directly calculate the gradients at the adjacent cell centroids, that is partial phi, partial eta at P and partial phi, partial eta at E, right? Calculate it at this location and at this location and then linearly interpolate them. Okay, so we take the first approach here in order to understand. So in the first approach, we can write phi A as phi P plus phi east plus phi southeast plus phi south, okay, divided by 4, because we are saying this is a uniform mesh. Okay, if it were not a uniform mesh, then you would get, instead of 1/4, you would get these lengths, right, that are multiplying these length ratios that are multiplying phi P, phi east, phi southeast and so on. Okay, similarly phi B can be calculated as 1/4 of the neighbors, that is phi P, phi east, phi northeast and phi north. Okay, so essentially we got values for phi A and phi B from linear interpolation. Now, what is the definition for partial phi, partial eta on the east face? That is nothing but phi B minus phi A upon delta eta, right? So that is partial phi, partial eta equals phi B minus phi A by delta eta. Now, we plug in what is phi B and phi A from the values we have obtained before. That means we plug it in these two. Then this would give us to phi P gets cancelled when you say phi B minus phi A here. Phi P gets cancelled. Similarly, phi E gets cancelled, and we are left with these two quantities with a positive sign and these two with a negative sign, right? Divided by 4 times delta eta. So what we get for partial phi, partial eta on the east face is 1 upon 4 delta eta times phi northeast plus phi north minus phi south minus phi southeast. Okay, that's what we get. All right. Fine. So this is what we got for the secondary gradient, that is partial phi, partial eta on the east face, which is 1 over 4 delta eta of phi northeast, phi north minus phi southeast minus phi south. Okay. Now, what do you notice in this equation? Does this equation look fine? Well, it is fine from mathematical approach point of view, but is it fine from our finite volume method point of view? What about the coefficients for phi S and phi southeast? Do they look okay? Do they look fine? No, they don't look fine, because there is a negative coefficient that is multiplying them. That is, the coefficient for phi southeast would be 1 by 4 delta eta, right? So similarly for phi south would be 1 by 4 delta eta. So this negative coefficient is not good for us, because if we have negative coefficients, then what it means is that if this value goes up in the previous iteration, then the value of phi P, right, which is basically calculated because of partial phi, partial eta, can go down because of there is a negative sign, right? So essentially this kind of behavior is not encouraged in our finite volume, especially when you're solving the diffusion equation alone, right? So essentially this will lead to oscillations, and this is the reason why boundedness is not guaranteed, right? Because an increase in the value of phi southeast or phi south could lead to a value, a decrease in value of phi p at a next iteration, right? So this leads to oscillations, and as a result, the boundedness property is not guaranteed. If you go back, all the coefficients we had before were all positive, right? If you look at AP phi p equals AP phi p equals sigma A and B, phi and B plus B, all the A and B's were positive, right? But that is not the case here, which will lead to oscillations. So that is the reason why we said boundedness is not guaranteed if you have secondary gradients. That means if you have a non-orthogonal mesh, boundedness is not guaranteed, okay? But then that is not so bad. So let us see what is the total value of the secondary gradient. It is not just partial phi partial eta, right? So essentially if you go write what is the secondary gradient value, that is SGF equals minus gamma f AF dot AF by AF dot xi dot E eta partial phi partial eta on the face east, right? This is the total value of the secondary gradient. That means the magnitude of secondary gradient is proportional to, so whatever you calculate here times this guy times is proportional to xi dot E eta, right? This is the controlling factor which will contribute what percentage of the value of the secondary, the partial phi partial eta goes into the secondary gradient, right? So for example, if you have an orthogonal mesh, this is of course 0. That means whatever you calculate doesn't go into the property at all. But if you have a non-orthogonal mesh, then if you have a good quality mesh, then this will still be very close to 0. Let's say it's 0.1 or 0.05 or something close to 0. As a result, the secondary gradient's influence will be very small on the solution for good quality meshes. Okay, so that is one reason why you should have a mesh that is as much orthogonal as possible in almost all the cells. Okay, so that is one reason to avoid boundedness problems. Therefore, but anyway, even if it is small, effect is small, the boundedness is not guaranteed because it depends on the quality of the mesh. So it is not absolute. For example, in the context of orthogonal meshes, we said boundedness is always guaranteed, right? Irrespective of the mesh. I mean, of course, the mesh is always orthogonal, okay? So, but in the context of non-orthogonal meshes, boundedness is not guaranteed. But if you have a good quality mesh, the influence of secondary gradients is small. As a result, you would not get very large oscillations in the solution, okay? So that is the influence of secondary gradient. Alright, so that answers our first question, why boundedness is not guaranteed if you have a non-orthogonal mesh. Let us move on to the second question that we wish to answer in this lecture today. That is, how do I program for diffusion equation on unstructured meshes? Well, of course, one way is to go about the way you are doing it right now. I mean, for structured meshes, that is basically again start off with the equation AP phi p equals sigma A and B phi and B plus B, and write such an equation for each and every cell, right? So for each and every cell, you would write such an equation, and then you will go cell by cell. You will start from, let's say, cell 1 that you have, and then move on to cell 2, cell 3, and so on. And when you go to every cell, you would calculate what is A and B. Let's say cell 1 has 4 neighbors. You will calculate what is A1, A2, A3, A4, all these 4 neighbors, and then you would calculate what is AP. You calculate what is B, the contributions coming from the source terms, and then you assemble this equation, right, numerically. And then once you have all the equations, you can use some method, Gauss-Seidel or something, and solve for it. But what we see is that this is not a very good way, or it's not an ideal way if you have to code up for an unstructured mesh. Okay, why is it so? One is from the calculation perspective, the other is from the solution perspective. Okay, so essentially from the point of view of the algorithm or what we have devised, it is better to do it in a different way rather than visiting each and every cell. And also from the point of view of calculations, the number of calculations involved can also be reduced if you do it in a different way. Okay, now essentially coming back to this question, how do I implement solution of diffusion equation on unstructured meshes? Now, in order to understand this, let's first take a look at a structured mesh. Okay, so I'm basically looking at a structured mesh that is one dimensional, okay, but that is non-uniform. You can see the widths are all different for every cell. Now, what we see here on the top is the same mesh as what we see at the bottom. Okay, so these are basically the same mesh. Only thing is that in the top row here we are solving for the P cell, that is this bigger cell 1, and in the bottom row here we are solving for this neighbor of this guy, that is 2. This is our primary cell. Okay, so that's what we are solving for, and the deltas for these cells are delta xp and delta xc. These are the widths of the cells. Okay, and similarly when you are solving for P phase, we have east and west, and the neighbors are east and west for the P cell, and of course this cell is east to the east, so we call it east east. And we are here for the second cell. This is basically the primary cell. Then this is our east cell, this is our west cell, and this is our west of west. Okay, so we just change the nomenclature here, but it is the same mesh we are talking about in both of these things. Okay, and then the distance between the P cell and the E cell is delta xe. Okay, so let us see, if you are writing if you are discretizing the cell 1, what is our A east? What is our A east? A east is nothing but gamma E delta y by delta xe, right? So that is gamma E on the face, and delta y this height, and delta xe is this distance. Okay. Now when you are done with cell 1, when you go to cell 2, what would be the coefficient for A west? A west would be gamma west, that is on this particular face, delta y this height times delta xw, that is this width. Now what we see is that we are just calling with a different name, but the numerical values of these are same as what we had before, because we are referring to the same phase, right? So essentially AW is nothing but same as gamma E delta W delta Y by del XE, right? It's basically the same phase, same distance, same gamma we are referring to, but it is now going into the coefficient for west coefficient for the next cell, right? So that means we are actually duplicating these calculations, because we are using the same numbers, calculating the same fraction, and then doing it twice. Once when we are at cell 1 and we are calling it an A east, and second one when we are at cell 2 and we are calling it A west. Okay, so we don't have to do this thing. If I can do it once for the phase and kind of send this contribution to the neighboring cells, then I can actually save one multiplication and one division here, right, which are extra, which need not be done. That will certainly speed up the calculation. And also there is another way to look at this thing. This is basically what we are saying is that these coefficients have come out to be the same because of some underlying principle. What is the principle? Basically the conservation of fluxes, right? Whatever is the flux that is leaving here is entering this cell. That's why these coefficients have come out to the same, right? Because your gamma grad phi on the face is basically leaving from cell 1 and it's entering cell 2. That's why it is the same flux that left cell 1 entering cell 2, and as a result the coefficients are the same. Okay, so what we just looked at is basically both the cells have the same contribution. So instead of calling them with east and west, we could have defined AF, which is basically calculate gamma F delta y upon delta XF. Okay, and the same AF can be given contributed to as A east for cell 1 and A west for cell 2, right? We could have done that. That is essentially what we plan to do, or what we do for unstructured meshes. Okay, so once I think this part is clear, the remaining things are straightforward. Okay, so let us move on. So what this kind of discussion suggests is that we can associate the coefficients with the faces rather than with the cells, right? Instead of calling A east and A west to belong to the cells, we can say that these actually belong to the faces, right? The common face defines what will be the coefficient for east and what will be the coefficient for west. Now let us look at the discrete equation. So in the derivations we got this discrete equation, which is sigma f gamma grad phi f plus sc plus sp phi p times delta v equals 0, right? So this is the flux right, that we got. So for any phase, the flux gamma grad phi is leaving the cell P and entering the cell east, right? That's what we have. It's basically conservation of fluxes times the source term is balanced, right? That is the conservation statement. Now instead of having a structured mesh, if you have an unstructured mesh, then gamma grad phi for a particular phase is leaving the cell C0 and it is entering the cell C1, right? Or it is leaving the cell C0 and it is entering the cell C2, right? Some other cell, and so on. Okay. Now this is because of the statement of conservation, right? Because the same flux is whatever is leaving cell 0 is entering cell C1. Now associating the fluxes with phases, right, rather than with the cells requires, of course, this requires you to maintain a list of your phases. That means you need to have a phase based data structure. Let's say up till now you only had a cell based data structure. For example, you had, okay, I have 10 cells, so I will call my A east with A east of 10, in which your 0, 1, 2, all these things led to different cells. Now you would call them as phases as well, right? You need to maintain a phase based data structure. That means you need to know what is the phases you have and which phases have what cell neighbors, right? For example, phase F has some cell neighbor C0 and cell C1. Next phase F2 has cell C0 and cell C2, and so on, right? So that connectivity information you need to know when you're dealing with unstructured meshes. Okay, let's say we know that from some mesh generation software or whatever you write. Okay, now of course this method of associating the coefficients to the phases rather than to the cells saves us from multiple calculations of the same quantity, right? Because this gamma grad phi that we calculate for one phase is basically going into two different cells. Okay, so that way we can save computation. Let's say per cell we can save maybe in this context we can save like one multiplication and one division, essentially two floating point operations. Of course, it depends on if it is unstructured, you have more terms here to evaluate as well. Okay, and also it is prone to lesser errors because now you have the same flux that you calculate is going into both of them, so it is kind of prone to less error. All right. So with this motivation, now let us look at how do you calculate the A neighbor. Okay, so A neighbor is basically if you have a structured mesh, that is as shown in equation 4, A and B equals gamma F AF by del XF. Okay, that we have already seen. But if you have an unstructured mesh, what will be your A and B? A and B is basically coming from your primary gradient coefficient, right, from the primary gradient term, that is A and B equals gamma F by del xi F times AF dot AF by AF dot xi, right? That is your primary gradient coefficient, that is A and B. Okay, now we can of course calculate A and B for a phase F that is between cell C0 and C1, right? Just like we have calculated for cell P and cell east, we can calculate this for a particular phase, because when I am in a particular phase, I know what is gamma on the phase, I know what is delta xi, the distance between C0 and C1, I know what is AF bar and xi. Now once I know all of these things, I can calculate what is A and B. Now this A and B contribution has to be given to both the cells that share the phase, right? So these cells C0 and C1 share the phase. So this A and B I calculated up in equation 5 here. I would simply assign it to the A and B of C0 cell, and also I will assign it to A and B of C1 cell, right? So essentially these two are different. This is A and B for C0 cell and this is A and B for C1 cell. Okay. Now see, we are not going cell by cell. We are going by phase, and we are accessing cells from the phases, right? That's what we are doing. Okay. Okay, that is so far so good. So we found a way how to do this thing. Now let's say we have an unstructured mesh that is shown on the left hand side here, something like this, where C0 is the primary cell we are focusing on, and then we have these three phases, that is F1, F2, F3, and which share cells C1, C2, C3. Okay, so that means when I calculate AF1, I need to assign that value to A and B for C0 and A and B for C1. A and B, we mean A and B for C0 to C1, and A and B for C1, we mean C1 to C0, right? For example, this A and B can be A01, right? That is basically coefficient of the 0 for one cell, right? Similarly, this can be A10. This could be coefficient of one first cell to the 0th cell, right? So that is A and B for C1. We will assign this for both the cells. Similarly, when we go to the next phase, F2, we calculate what is AF2 from the original expression, that is gamma F by delta xi F, AF dot AF by AF dot xi, and then assign it to A and B for C0 and A and B for this is for A and B for C2. This also should read C2, okay, not C1. All right. Now, what we see here is that the magnitude and sign of A and B is the same for both the cells, right? AF1, we are not changing anything. We are assigning the same value to both C0 and C1. Similarly, whatever you calculate for AF2, we are assigning it to C0 and C2, right? We are not changing. Why is this? Why is this? Actually, this is happening because although we calculate from A and B from this cell, when we go here, there are certain things that are changed, right? For example, your AF now points this way and so on. So this contribution is the same for both cells, because if we look at let's say two triangles in isolation, that is on the next page here. Okay, so here we have C0 cell, C1 cell, and the black lines here indicate, the black arrows indicate the entire nomenclature AF bar, xi, e eta with respect to C0 cell, that is also shown in black, and the blue lines indicate AF bar, e eta, xi with respect to C1 cell. So how would you draw this when you consider C1 as your primary cell, and how will you draw this when you consider C0 as your primary cell? Okay, so that is what is black and blue lines indicate. Now we are calculating A and B that is basically we are calculating AF when we are sitting on C0, right, with respect to C0, because let's assume that we are calculating with respect to C0. That means our xi points in this direction, the black direction, and AF points in this direction, and then we calculated some A and B. Now that A and B we are saying is the same as the A and B you would calculate when you are sitting on C1 and you calculate from F, because when you calculate from C1 perspective, for this F, AF actually points this way and your xi now points this way, right? But this would come out to be the same, because if you go back to this calculation, what is the primary gradient contain? A and B contain gamma F. This is the same for both the cells, whether you sit on C0 and C1. Delta xi is the same. What about AF dot AF? AF dot AF, although it is changing direction, right, from black to blue, but this magnitude is always the same because they're squared quantity. Now what about AF dot xi? AF dot xi is something that we have to look at. AF dot xi, when you calculate from C0, is basically pointing this way and xi pointing this way, right? So there is some acute angle between them. Now when you switch to C1, what would this be? This would be AF is pointing this way and xi is pointing this way. So both of them flip their sign as a result, and they maintain the same angle, right? As a result, AF, the dot product of AF and xi would come out to be the same, and as a result, whatever we calculate on the face with respect to either cell would be the same contribution for both the cells, right? That is basically A and B would be the same whether you are sitting on C0 and calculating it or C1 and calculating it, because AF dot xi, both the vectors change sign, and as a result this will come out to be the same. Okay, that is something you have to verify once again. Alright, so because both AF bar and xi reverse directions, when we move from C1 to C0, this quantity A and B would remain the same whether you calculate from C0 side or C1 side for the phase F. Now what we need to do, we need to of course visit each and every phase in this fashion. Once you visit each and every phase in this fashion, when you finish visiting all the phases, that completes the calculation of A and B for all the cells. For example, this cell has one AP, that is A0, and it has 3 neighbors, so they will have A01, A02, A03, right? 3 neighbors, but 3 neighbors will be populated when you have already visited F1, F2 and F3, right? Similarly, once you visit all the faces, then for every cell, their neighbor coefficients would have been filled already, right? By the time you finish, you have filled all the neighbor coefficients for all the cells, right? Do you see the difference? If in the original cell-centered or cell-based approach, you would go to every cell and populate the neighboring coefficients for every cell. But in this case, you are visiting faces and populating in pairs the neighbor coefficients for those cells which are sharing that face, right? So the pattern is different, but once you finish visiting all the faces, you have already assigned all the cell neighboring coefficients. Okay, this is faster. Do you see why this is faster? Because you are not calculating again for every cell, and also you are assigning both of them at once, right? Rather than going here and calculating 3 and coming here and calculating 3, you are going here and assigning 2 of them, right? So by the time you finish 3 phases, you actually assigned 6 coefficients, right? Okay, fine. All right, then let's move on. So this is about the primary gradient, right? We are talking about a non-orthogonal mesh. Then you also have the secondary gradient coming into play, right? Because we said implementation on unstructured meshes, you have gamma grad phi can be written as some coefficient times partial xi plus some coefficient times partial phi partial eta, right? So you have these two. So we have already looked at how to deal with partial phi partial xi. Now what about the secondary gradient? Now how do you calculate this term for the cells? Of course you can go to again every cell and calculate, but that is not the motivation. We want to calculate it from the phase based data structure, because Sg is also associated with the phase between the cells, because that's why we write secondary gradient sub f, right? So this is also associated with the phase, so it would save us computation time if you can calculate it once and assign it to both the cells that share the phase. Okay, so where does the secondary gradient term go in the equations? So we know the secondary gradient is minus gamma f af dot af by af dot xi times xi dot eta partial phi partial eta f. Now where does the secondary gradient term go? Does it go into the matrix A? No, it doesn't. It goes into the right hand side, right? That is the B term. It goes into the B term. Okay, fine. Okay, so SGF goes into the B term. That means the B term also contains not only the secondary gradient term but also other quantities. What are the other quantities that the B terms for the cells contain? They contain the source term SC times delta V, of course, and also they also contain some contribution from the any Dirichlet boundary conditions if you have, right? So those also will go into the B term. So as a result, we cannot simply assign the secondary gradient to the B term of any cell. Rather, we have to add to the existing B value. Okay, therefore instead of assigning, add to the existing value, because the B term might also already contain some values from the boundary conditions, from the source terms and so on. Okay, so you cannot override it with only the secondary gradient term. Okay, so as a result, I would calculate what is the secondary gradient term for a particular phase, and I would add that contribution to the C0 cell. I will add B equals B, the existing value of, let's say, source terms, Dirichlet boundary conditions and so on, plus secondary gradient. For cell 1, I would subtract this secondary gradient from whatever I have calculated for the particular phase while sitting on cell 0. Why do I subtract it here? Why not add it just like the primary gradient? Okay, so this is again goes back to the figure. Okay, we have this figure where the black lines are all definitions for AF bar, xi, eta for C0 cell, and the blue lines are the definitions when you are sitting on the C1 cell. Okay, now what is we are only calculating, let's say, from one cell, and then we are trying to assign it for both the cells, right? That is the issue here. Now one thing we have to keep in mind is that we are keeping the E eta direction the same for both the cells. Okay, I am assuming that E eta is the same direction as we have had before. This is one assumption we are doing. Now what about the secondary gradient term? So gamma f doesn't change for the cells whether you're sitting on C0 or C1, you calculate this is the same. AF dot AF doesn't change, the same thing. What about AF dot xi? AF dot xi, both of them change sign, so as a result there is no problem. So this entire thing remains the same. That's why our primary gradient was coming out to be plus sign for both of them. But what about xi dot e eta? What about this quantity? This we have to see. What about partial phi partial eta? This quantity would remain the same, right? You would calculate from phi A and phi B and calculate the gradient. This is the same for whether you calculate from A cell or from B cell. Okay, what about xi dot e eta? So xi dot e eta, when you are calculating from C0 side for the phase F, xi is pointing this way, e eta is this way. Whereas if you have, let's say, gone to the next cell and tried to calculate secondary gradient for this phase, then xi would point in this direction and e eta would still point in the same old direction, right? Because we are assuming that it points in this direction. As a result, what happened to the angle? Earlier xi dot e eta had this angle here, some acute angle. Now xi, it's some obtuse angle, and then now xi dot e eta has this angle, right? So there is a change in angle here by 180 here. So as a result, xi dot e eta would change sign when you go from C0 to C1 because of the assumption that e eta is still pointing in the same direction. Okay. So as a result, you have to add it to the B0 cell and subtract it from the B1 cell. Right? Is this clear? So when you move, we are trying to calculate f from one cell and assign it to the both cells. Right? So as a result, all these terms will remain the same except for xi dot e eta. Okay? Xi dot e eta is flipping because xi is flipping but e eta is not. As a result, xi dot e eta would give you a sign change which needs to be accommodated in the calculation. So because SGF is calculated from C0's perspective, that's why we are subtracting it off here, right? Of course, if you calculate again, go back to C1 and calculate, then this will be plus only, right? That we are not doing here. Okay, so that means the primary gradient can be directly assigned, but the secondary gradient has to be added to one cell, the B term of one cell, and subtracted from the B term of the other cell. Okay, so that's what we kind of discussed till now. Fine. Then what we assume is that through the grid generation software or through the cells we create, we have a list of phases in the mesh that we have generated. That means we know either through an array or through a linked list what are the phases we have in the mesh. Now the cell neighbors for these phases are also maintained. For example, you go to a particular phase, you know who are your cells, C0, C1, and go to another cell, you know who is your C0, C2, and so on. So, and also we have a list of cells in the mesh. Okay, that means either through an array or a linked list, we maintain a list of cells. Now these cells are formed because of the phases. So we can go from cells to phases and phases to cells, okay, in terms of the connectivity. Fine. Alright, so having given that we know all these three that we have, then how do we approach in writing a solution algorithm for unstructured meshes? Essentially, you visit all the phases, and when you visit every phase in the mesh, you calculate what is A and B, what is B for the cells, right? And then assign it to A and B for both the cells, and B, once you calculate what is secondary gradient, you assign it to one cell, add it to one cell, subtract it from the other cell, and keep doing this. Once you finish visiting all the phases, you have got A and B calculated for all the cells, and B, the contribution of secondary gradient, is also added for all the cells, right? That is done. Then what we do is we will not visit, then we will not go to the phases, we will go to a list of cells. So we visit each cell and we calculate AP. Okay, how do I calculate AP? Now every cell got A and B is populated. So I can go simply sum all the A and B's that cell has, and that summation minus SP times delta V naught will give me what is AP, right? Of course, this has to be modified if you have a boundary condition, a cell that is near the boundary, okay, because your contributions would change, right? Because you would have, if it is a Dirichlet, you would get an extra quantity here and so on. Okay, that has to be done. We are talking about an interior cell in this particular context. All right. Now, then visit each cell and calculate the contribution of SC and add it to the B term, right? The B term now already contains the secondary gradient component. Now add SC times delta V naught to the B for every cell. Okay, now we are going cell by cell. So when we visited the faces, we populated the A and B's and B's. And then when we are going by cells, we are calculating what is AP and what is updating B for every cell, right? Alright, so till now there is no duplicacy as such, right? We are doing everything once and then using it as much as possible. Now, of course, the secondary gradient F needs gradient calculations, and grad phi at cell centroids. These were somehow already calculated before we go to this step, right? Because you already know what is your calculate what is grad phi before this step, and then using grad phi you have calculated what is SGF, and then you populated A and B and so on, right? Now, of course, these equations have to be modified if you have to incorporate the boundary cells, right? If you have to incorporate the Dirichlet boundary condition or Neumann boundary condition, these have to be changed. I think that we understand. Okay, fine. So that is the overall algorithm. Let's look at the complete algorithm as it stands for solving diffusion equation on an unstructured non-orthogonal mesh. Okay, so what do? Initially we start off with phi at the cell centroids, right? That is the first step, because if you want to use an iterative based method, you guess what is phi at the cell centroids and also at the face centroids, where you have to apply a Neumann boundary condition, right, or a mixed boundary condition. So the first step is to guess phi at the cell centroids. Now the second step is basically calculate gradient of the phi. Why do we do this thing? Because we need this in the secondary gradients, we need this in all other terms that might go into B, right? So using either gradient theorem or using least squares method, you calculate what is grad phi. So once you, with the initial guess that you have. Alright, then we calculate all the coefficients. So for calculating the coefficients, we first traverse through the faces. So we have a list of faces. So if I use face here as my index I, so I'm going from phase 1, 2, 3 and so on to n phases, which is basically the total number of phases I have in a particular mesh. Okay, so that's what we do. We traverse through the phases one by one, and when we are at the phase F, we calculate A and B, that is we calculate AF and assign it to both the cells C0 and C1 as it is. Then you calculate what is secondary gradient and you add it to the C0 cell, that is B0, and you subtract it from the B1 cell. B1 equals B1 minus secondary gradient of F, B0 equals B0 plus secondary gradient of F. So we do this thing. This is basically calculating the coefficients and filling them, right? That is done. Then we are done visiting all the phases. What do we do next? Next is to look at cells, right? So we go to each and every cell, right? Traverse through the cells. For cell is my index here, okay? Some kind of I or J, 1, 2, 3 and so on. So cell, go from first cell, second cell, third cell, and all the way to n cells that you have. And here is where we're calculating the central coefficient, that is AP. AP equals sigma A and B, which were already populated in a visit to the cells through the phases, minus SP times delta V, right? This is basically the source term that is going into AP. Now, of course, we have to also add the B term, that is B plus SC delta V, right? This is what we do for the B term and AP term when we are visiting cells. All right. That means now, in a way, by calculating A and B, B and AP, we have actually formed this equation in a virtual manner, right? We have nowhere written this equation as it is, but we have updated these values. That means we have this, everything that we want in this particular equation to be solved, right? That means we have AP phi P equals sigma A and B plus B. All the coefficients are known, and also the phi and B's are known from the guessed values. So we are now ready to solve this equation for phi P for every cell for this particular iteration, right? Essentially, we can use Gauss-Seidel or Gauss-Seidel successive over relaxation or under relaxation, and then calculate what is phi p for the entire cells, right? Now, once you do that, you check for convergence. Check for convergence meaning you have two convergences. Essentially, here you converge everything. You solve for phi p not changing between iterations. Now, that phi p you check it with the whatever is the guessed value in step 7, right? Now, this of course would not be the same. So it would, so although the Gauss-Seidel has converged, this would be different because the guess value will be different from this converged value. Then if it is not the same, then you go back to step 2, right? Step 2 is what? Then with the new values that you got for phi, you calculate grad phi and then follow down the same process and then again solve for Gauss-Seidel, obtain new phi values at all the cell centroids and move on, okay? Now you see here there are two iterations, what we call as inner iterations, which are basically for solution of the Gauss-Seidel, right? This is, let's say, some 1000 iterations. These are all the inner iterations. Now once you come out, you are doing this, if not go to step 2, this is basically the outer iteration, right? Which is basically telling you that you have to keep doing this for several iterations until you converge to some value. Now we are talking about a steady diffusion equation only, right? But we still have two iterations. That is because we are using an iterative method for the solution. The other one is because we have a non-orthogonal mesh. Right? Now these outer iterations are required if you have nonlinearity in your problem, right? If you have nonlinearity, you need these outer iterations anyway. Okay, that is one particular case. If you have a linear problem and if you have a orthogonal mesh, then you don't have to have these outer iterations, right? Because everything you're solving for is correct. But if you have still a linear problem, but if you have a non-orthogonal mesh, then you still have to have outer iterations because the secondary gradients are calculated in a deferred correction method, right? We are calculating the secondary gradients. The grad phi is calculated with the guess value. So as a result, even if you have a linear problem, if you have a non-orthogonal mesh, then you would still require outer iterations, okay? But if you have a linear problem on an orthogonal mesh, then you don't need the outer iterations, okay? Is that clear? The need for the outer iterations. So the need for the outer iterations is even for steady state problems, either nonlinearity or non-orthogonality would demand the outer iterations. Fine. All right. So that is how you would code diffusion equation on an unstructured mesh that is either orthogonal or a non-orthogonal. Okay. So this could be a good method to implement. Yeah. So for your project, maybe let's see. Okay. So concluding remarks are basically in this lecture we learned about how secondary gradients create unboundedness. And then how do you program for diffusion equation on general unstructured meshes using a phase-based and a cell-based data structure approach. Okay, so we have answered these two questions in today's lecture. All right, and this kind of finishes our chapter 3 on the diffusion equation. Okay, so we have discussed all the structured, unstructured meshes, steady, unsteady diffusion equation, and we have looked at the stability and the accuracy, all these things for the diffusion equation alone. Okay, so in the next lecture we are going to start the next chapter, that is chapter 4, that is for convection and convection diffusion. Okay, so that will be our discussion for next lecture. All right, so I'm going to stop here. Thank you. If you have questions, write back to me. We can discuss them. Okay. Thank you.